Hello friends, now I am going to solve this year 2022 UPSC Geo-scientist chemist Prelims paper. So we know that in chemist for the post of chemist in the Geo-scientist examination in Prelims there are all total 120 questions, and the 40 questions are from organic chemistry, 40 from inorganic chemistry, and 40 from the physical chemistry. Right now I am going to solve 10 questions from this paper in organic chemistry. Okay, and we know that organic chemistry question starts from 81 and goes till 120. So I'll solve one by one from 81 to question 90. Okay, now the first question here came: which one of the following statement is not true? So also careful about these words where they are saying not true, not correct. So we actually miss sometimes, so don't miss this kind of words. You might know the answer but can end up doing it wrong, so be careful about it. So there are two molecules given. It looks like they are similar, but I'll come to that point. So they are asking not true, which statement is not true. Now these two structure, this is cyclooctatetraene substituted, 2-methyl substituted, and as we know that cyclooctatetraene, so if we write the structure here, draw it this. Okay, so here in this molecule there are actually 8 pi electron all total, 4 double bond, so 8 pi electron. And we know if the molecule is in the plane and the pi orbital in the conjugation, it will attain 4n pi electronic structure, 4n pi electronic structure, which is anti-bonding as per Huckel. Okay, so as per Huckel it is, and it will be anti-bonding, so that anti-bonding is destabilizing in nature. So this type of molecule, this cyclooctatetraene, do not prefer this anti-bonding destability. That's why they escape from this anti-bonding by twisting into a tub shape. So where this molecule actually breaks its planarity and goes into this type of structure. Okay, so this is a tub shape, like the double bonds are not in plane, so there is no conjugation. So this is actually a non-bonding structure, which is actually stabilizing in nature. You can find like this is roughly 18 kilojoule stabilized compared to the anti-bonding structure. So for the structure 1 and structure 2, if they are conjugated, then the structure both will be in the conjugation form. This will be as like benzene, this will be the same structure, so they will be resonating form. But as I have shown to you, this is not actually. So the structure 1 and 2 are simply two resonance form of the same molecule. So this statement is wrong. They are not resonating form of the same molecule, so they are actually different. So they are not resonating. So this statement is true, not true, and they asked here the not true. So the option A will be correct. Now let's see the other option also. Now the structure 1 and 2 represents the different molecule. Definitely they are different molecule. Like see, in this tub shape, if you put the substitution here on a single pi double bond, so for that is the structure 1. But if you put another substitution, not here but rather in this position, so they are in the adjacent carbon-carbon bond, carbon-carbon molecule, but not in a same double bond. Okay, so that is the structure 2. So they represent different molecule. Definitely they representing different molecules. So this statement is correct, but they didn't ask the correct statement. Now 1 and 2 are non-aromatic in nature. Yeah, as I said that they are not aromatic, they are actually breaking that planarity and going to non-aromatic structure. and the anion of 1 and 2 are aromatic in nature. Now you see that's 4n pi electron anti-bonding gives, and we know that 4n plus 2 pi electronic structure, this is 4n plus 2 pi electronic structure gives bonding, aromaticity as per the Hooke's law. So this cyclooctatetraene can be reduced by electron, and that is from sodium in liquid ammonia. So you know that this is a very good reducing agent because the electron is free and solvated in the ammonia, and if it will take 2 electron from this solution and will be reduced into this form. Okay, the structure will be like this, dianionic form. So this is 10 pi electronic system which is aromatic, and to attain this aromaticity they actually come into plane. This molecule is the planar here. So the dianion is aromatic. This statement is also true, this is also true, but the option A is correct. Now move to the next question, 82. Rank the following dienes in order increasing heat of hydrogenation. We know that heat of hydrogenation is the enthalpy change when a compound reacts with an excess of hydrogen. So to become fully saturated, so the end product for these 3 molecules given here are same. This complete saturated product is the same. So the heat of hydrogenation will depend on the stability of the alkene, and we know that the enthalpy of hydrogenation is inversely proportional to the stability. Now we have to check the stability, and they actually ask in the increasing order of the heat, so we have to actually arrange them in the decreasing order of their stability, and that will in turn reflect the increasing order of heat of hydrogenation. Okay, now we know that conjugated double bonds are more stable than non-conjugated one. We can find that the 3 and 1, these 2 are conjugated. Okay, now among these 2, the 1 is more substituted, so definitely 1 is more stable than 3, and 2 and 4 are less stable compared to 1 and 3, but among 2 and 4 the 2 is more substituted compared to 4. So the order will be 1, 3, 2 and 4. So that is D, 1, 3, 2 and 4. This will be the stability, this will be the decreasing order of the stability, and in turn increasing order of heat of hydrogenation. Okay, understood. Now come to the next question, which is, this is a very simple question. Yeah, you can easily solve it. The hybridization of the nitrogen in this imine. Okay, as we know that imine nitrogen is actually sp2 hybridized. You can very easily actually calculate it, and also can see it. Actually, this nitrogen is having double bond with the carbon, and the vacant p orbital is perpendicular to the plane, so to this nitrogen. Okay, and this lone pair is in this sp2 orbital. This is a sp2 orbital. Now if you really want to actually calculate the hybridization of this just by applying a rule, so you can then also calculate. So half of that so of the central atom, and the nitrogen's valency is 5, we know, and we have to add the number of monovalent atom attached to it. So the actually single bond, not monovalent atom, single bond. So one single bond actually. So carbon, this single bond, this is a double bond. Okay, if we took one monovalent, then in that case 2. So but we ultimately have to take only the single bond, so that's why 1. Now this is 3, and you know, if you get 3, then this is in turn gives or suggests you this hybridization is sp2. So the option is P, which is correct one. Now 84, they are saying that indicate the CH bond, indicated CH bond. So bold CH bonds are here. Each of the following pairs of the compound would yield a more stable free radical upon homolytic cleavage. So these indicated single bonds are going to be clipped by homolytic fashion, and this in turn will give you the free radical. Now, and you have to indicate the stability of that free radical. Okay, more stable, so yield the more stable free radical. Now from 1 and 2, from 1 you will get benzylic radical in this position, and we know that benzylic position through the mesomerism gets more stability compared to the phenylic one. Okay, and phenylic free radical is not actually stable, because if you draw this structure like this, you will get the free radical structure where the orbital containing that single electron is actually in the perpendicular plane of the p orbital. So p orbitals is in the above and below of this space, and here this orbital which is containing the single electron, that is the radical electron, is in the perpendicular position compared to that benzene conjugated pi electronic cloud. So it is actually not going into the mesomerism of that benzene ring, and that's why no stability is coming from delocalization, which is actually the case for the compound 1. Okay, so 1 is definitely stable among the pair X, and among the pair Y, 4 and 3, where the 3 will be more stable, because you know both will give you the 2 degree free radical, and we know that radical stability increases from when we go from 1 degree to 2 degree to 3 degree. We know that with the increase of that substitution, the radical stability, alkyl substitution, this stability increases. So here the 3 will be stable, so 1 and 3 will be the option. Now moving towards the next question, 85. The mechanism of the reaction at the stage 1, stage 2, stage 3 in the following reaction sequence. Now this question is very easy. You need not to even know the mechanism of this question. This is actually a cumin phenol reaction. In this, if you see at this stage 2, you can understand that. But even if you do not know the mechanism of this question or the course of this question, you can very easily solve this question. Like the answer asked here, so the steps, are they polar or radical? Now we know that for radical formation we need to have some radical initiator or something which can form radical. Now if you look at the first stage, stage 1, where the H2 support, we know H2 support is an acid which can protonate something. Okay, like if something giving H plus, it's not definitely making it is not a radical initiator, or this is kind of cationic or anionic, or like just reaction mechanism where you will protonate something, making it positively charged. So that's why that will be polar in nature, that reaction course. But we know that oxygen is inherently free radical, because electron pair in the oxygen, so we know that electron pair in the oxygen is actually in the antibonding orbital, where the each two electron in the pi star actually reside separate, so they are actually unpaired. That's why oxygen in the normal stage, in the ground stage, they actually live in triplet stage. So oxygen is a free radical and they can act as a free radical initiator. So this is a cumin hydroperoxide will form here, oxygen will add, and then the cumin hydroperoxide will form. This is the cumin hydroperoxide, and later stage, in the stage 3, when the H3 plus is added, acid is added, then this cumin hydroperoxide OH will protonate and the neutral water will eliminate, and simultaneously the phenol group will migrate. So this is a kind of rearrangement reaction where you will get the phenol. So we can see that's the middle stage, stage 2, only the polar. So if you know it, if you can understand this, then in that case you can very easily eliminate this stage 2 radical. So this option, stage 2 polar, stage 2 radical, this option will be there, stage 2 radical, this option will be there, but stage 2 polar, this option will be eliminated, and stage 2 polar, this option will also be eliminated. Now among these you can also see that H3 plus added, so this will be polar, so it is actually, but the stage 1 is radical for the option A, but this is not the case here. H2SO4 do not lead to the radical formation, so that's why that is also polar. So here the option B is the correct one. Okay, now question 86, which one of the following molecule is chiral? Like, we know that chiral molecule which is not having improper axis of symmetry. If a molecule is having improper axis of symmetry, that is plane of symmetry, that is the sigma plane, or center of symmetry, that is inversion center I, then that molecule is definitely achiral. So we have to find out which molecule is not having sigma plane. You can see if we put sigma plane like this, the sigma plane passes, so this molecule is achiral. If we put sigma plane like this, like where the sigma plane is containing both bromine and CH3, then also this molecule is actually having the sigma plane, the plane of symmetry. So this option is also wrong, this option is achiral. And here also the same way, if you put sigma plane like this way, this molecule is also containing sigma plane. But if you put sigma plane like this way, this middle of this two, here the CH3, here the bromine, so they are not the mirror image of each other. So for this molecule the sigma plane do not pass, so this molecule is not containing either sigma plane or the center of inversion, so this molecule is the chiral one. Okay, which one of the following is not meso compound? So here also careful about it, the not meso, they are not asking which molecule is meso. You may find out something very first instance that this molecule is meso and you marked it, but yeah, here you can do it wrong. Okay, so be careful about it. So not meso, and we know that the molecule which is having sigma passing through the molecule, then the molecule is meso. Okay, but if a molecule is not having sigma, not meso. Like this molecule is clearly visible that this is the sigma for this molecule. Okay, OH, hydrogen, and CH2, CH3, CH2, CH3. So this molecule is not the is meso one. So not meso is not the option here. Like for this molecule, you can do two ways. So this is the sigma, this is the bond. You can rotate this bond and see is there any sigma plane, or you can also do the nomenclature R and S. We know that as per the priority, this is actually A, B, C. So, and hydrogen is the rear side, so A, B, C, it is actually clockwise rotating, so that's why it is R. Okay, now this is actually A, B, C, the hydrogen in the upside, so this least priority group, if upside, it will be opposite. Okay, So this is actually rotating clockwise, but it will be S. We know that if I put R before a mirror, it will reflect as S. So R and S in a molecule in the same configuration, actually the meso or the mirror image to each other, they are actually signaling that there is a sigma plane. So definitely this molecule is containing a sigma plane. Okay, so this is not, so it is actually meso. This is not the option. For this molecule you can do the same. Okay, you just rotate it, or you can do the nomenclature itself. If you find it RR or SS, then definitely this is not meso. But if you find it is RR, RS or SR, then definitely that is a meso. Like I'm not doing here that R and S nomenclature, I'm just rotating that single bond. So if I rotate single bond, so pH, this is Cl, if I rotate it, pH will be here, and the Cl in the downside it will come upside, so like this. Okay, but this Cl is in the downside. Okay, like if I now put sigma plane like this is not a sigma plane, because if the Cl is upside, it will reflect this side in the upside, not in the down. So this is not a sigma plane, and you nowhere in this molecule the sigma plane passing. So this molecule is not containing any plane of symmetry, and thus this molecule is actually not a meso. Okay, so the option C is the correct one. Okay, you can easily see that option D is also not, because there is sigma plane. It's very easy. Actually, this is not option. Now, question 88. The stoichiochemical reaction for the following compound are. Sorry. The stoichiochemical notations. Okay. So you have to do the nomenclature as per the UPSC nomenclature. You have to do the numbering first. So from the substitution, so you can see the longest chain is like this, or you can take this also, but okay, anyway. But numbering will not be from this side, because here there is no substitution at this carbon. Okay, you can find the substitution at this carbon. This is a functional carbon itself. Okay, so start nomenclature from this, from here 1 2 3 and 4. So now 2 carbon is having a double bond, and that will come up with a EZ nomenclature, and this is A, this is B, and this is A, and here there is a hydrogen, so this is B. We can see that A are in anti-orientation, in opposite, so that will give you E, so that is 2E. So among these two options, the answer will be, you have to do the other nomenclature for the center 4, which is a chiral center. The same way I did for the previous question. So this is A as per the priority. Now you have to check the priority of the other two center, this and this. Now here this carbon and this carbon is actually attaching. So if we break this double bond, you can do it like this. So here definitely one hydrogen is there, but if you break this double bond carbon, so definitely you can think there is a carbon as per the phantom carbon law rule. Now here is hydrogen, this is carbon, and attached with 3 other hydrogen. Now this carbon is attached with carbon hydrogen, so write it, this carbon hydrogen, and this carbon is attached with carbon, this carbon, then carbon, and then hydrogen. These two are same, this sequence are same, so then you have to move to the next for the carbon. Now you have to see for the first carbon, what's the carbon actually having the substitution. Now for this, take any other the carbon, then this carbon is having hydrogen, this carbon is also having hydrogen, so take hydrogen, and hydrogen. But if you take this carbon is this one. Do not take this carbon at the very first instance, because here you will get 0 0 0. Okay, so take this carbon. So you will get this carbon is attached with okay, so this carbon is attached with carbon. That's the very first thing, carbon, and this carbon and Cl. Okay, so definitely you do not need not to understand the latter part, but you can see that after this carbon is having hydrogen, but this carbon is not having hydrogen, instead it's having carbon. So overall priority of this carbon is high, so this is will be B and this is will be C. So A, B, C, it is moving in a clockwise direction, but hydrogen in the upside least priority group, so this is will be S. Okay, so the answer will be D. Now question 89, which one of the following compound shows geometrical isomerism? Now we know that geometrical isomerism is actually cis and trans isomerism for a double bond, and isoprene do not show any geometrical isomerism. 2,3-dimethyl pentane, it's not. But cyclooctane, so you can think that cyclo compound, how can they form geometrical isomerism? Because for the cyclohexene we can see there is no such thing. This is only the cis is possible, but cyclooctane is the smallest ring that shows both cis and trans isomerism. So you should remember this. Actually this is very interesting, because cyclooctane is like this. The ring size is sufficient to get a trans form, which will be like this. Okay, okay, so this will be like this. This is the trans form. You can very easily understand. This is the trans double bond. So this is the trans form, this is the cis form. So the option cyclooctane will be the correct one. Now the 90, the eclipsed conformation of CH3CH2Cl is 15 kJ per mole and is less stable than the staggered conformation. How much is hydrogen and chlorine eclipsing interaction worth in destabilizing? Here hydrogen eclipsing interaction worth 4 kJ per mole. It's very easy actually. You just draw that Newman projection formula for this. Now for chlorine I am putting it upside. Okay, chlorine, then hydrogen, and then the next carbon, there's 3 hydrogen. So this is the staggered conformation. There is no eclipsing interaction. But if we go to the eclipse conformation of it, chlorine, hydrogen, now there will be hydrogen and hydrogen. Now you can see there is hydrogen eclipsing interaction, hydrogen eclipsing interaction, and hydrogen chlorine eclipsing interaction. So from staggered to eclipse you are actually increasing 3 interaction, and that's why actually the stability or decreasing. So the total actually interaction cost is 15 kJ per mole, but they have given that hydrogen eclipsing cost is 4 kJ, but 2 hydrogen interaction cost will be 4 into 2, that is 8, and if you subtract it from 15 you will definitely get 7, and that is actually hydrogen chlorine eclipsing interaction. So the option C will be the correct one. Okay, goodbye guys.